Good afternoon. I invite you to the seventh, I think, lecture from our basic computer architecture course. And today's lecture is about interconnection of the system with external world. Basically, to have not only a black box which crunch the numbers, but the system which can somehow communicate with the outer world. Again, I have there some motivation picture. It is from our countryside here, so it is spring. I hope that you can enjoy it and so on, and that weather will be good and so on. And now we get to the lecture outline. So we will speak about the input-output system introduction, and it is the part which you will test on Qt RVSim, so it is important part, and it is mandatory, so basically you should understand to this. There is memory mapped I/O and such stuff, so again it is important. Then we look at some examples on Qt RVSim, and then we start to speak about real buses. The topic of input-output subsystems is really huge, and it can cover more than one course also. Basically, it is quite complex area. Maybe some of you will have some another subjects which are focused on the communication and for the implementation of the peripherals and so on. So you probably will return in the future to those topics. And okay, this lecture is really huge, and I will go very quickly through the rest of the contents and focus on two areas. First, we look what happens with the parallel buses and why it is necessary to switch to the serial buses, where instead of the sequence of words, we send bits one bit after another without the external clock signal. So it is from the rest what you should understand, why we switch to serial and then to PCI Express. And then we will have their example how looks the transfer on the relatively old parallel PCI bus, but actual transfer of the data inside the CPUs and inside the system on chips uses parallel buses. So basically, ability to read the timing diagram for some parallel buses is important. So this is the reason why we have this example. On the other hand, PCI Express uses the same software view as a PCI, so I think that it is no big problem. And maybe if there is a time, we can look quickly to the enhancement of reliability of SSDs and so on, and the hard disk. Okay, so we still return again and again to this almost 100 years old diagram from von Neumann. In this concept, the input-output, which interconnects the computer system with the external world, is connected to the data path, and the CPU takes care about storing the input data to the memory and then to reading it back and providing it on the output. Today's systems usually allows setup of the peripheral such way that data are directly delivered to the memory, and then CPU is notified by some event, interrupt, and so on. And again, it can prepare a block of data and notify the peripheral that the data are sent directly from the memory to the output. And even those input-output instructions, which was originally a special separate set of the instruction, are usually on the modern CPUs combined to the common memory access operation, load word, store word, and ADC. So this is our, in this case, non-pipeline version of the CPU. And we have seen that we have in our idea and diagrams the memory shown as a separate instruction and data memory inside the processor. But when we move those two memories out and left there the address port and read data port for the instruction memory and for the data memory address information if the next access is read or write, and the write data port and read data port, then in the fact we can switch the vice versa, the internals and outer parts of the CPU. So at the end, we get to the standard concept when those signals for the address and data are provided on the pins of some chip or of some internal cores as a signal which interconnected to the internal interconnect network. You have seen that we have separate address for the instruction and data in our concept, but we can somehow multiplex them on the same pins to lower the number of pins. Then the accesses which read the instruction needs to wait till the data are provided and so on. So usually we have internally the hardware buses and the caches in the hardware configuration, but the actual access to the main memory and peripherals in von Neumann when there is only a single port where at the given moment only a single memory access is provided. For the FPGAs, we usually have separate signals and port for data read and data write. On the other hand, on the actual chips, those are usually combined to a single set of the signals to lower number of pins or signals and so on. Even the address and data can be multiplexed on the same set of the signals and so on. We will see some combinations later. For the parallel bus, we need some additional control signals. For example, in this case, there is shown a memory read, memory write. So basically, load word and store word activates those signals. You can see that in this notation, we have there a hash at the end, which in the fact means that signal in this case is activated by a low voltage level. So, or zero level is in the fact the active signal in this case. It is more or less given by history when old TTL circuit has drawn more power and higher power consumption at low voltage output, and they propagated switch from the high to low faster than switch from low to the high. Today, CMOS systems usually do not have this difference, but quite often we have there those signals activate at the low level. And we can have only those two, or we can add the additional separate for I/O accesses, that memory and I/O has different address space. Then we usually have some additional signals here for some control and to control the length of the transfer and so on. Because if we have 32-bit bus, but we still want to have possibility to address individual bytes, then we need to provide some byte-enabled signals which select which from those 4 octets on 32-bit bus, or maybe 8 octet on 64-bit bus are active for a given transfer. Okay, so this is the theory. If we look at the different peripherals and interfaces and so on, then we can categorize them from the behavior that some of them are input only. For example, you can say that keyboard is input only. In the fact, a keyboard usually needs some possibility to set up the repeat rate and set LED diodes and so on. So today the strictly input-only and strictly output-only devices are quite uncommon, but there can be such input-only. For example, some sensor on the robot is usually, for example, can be input-only. There can be write-only registers or write-only peripherals. Then we have there storage, which cannot be written and read by individual bytes, but we usually need to write a block of data, and then we have there a different kind of the communication and a different hierarchy of buses and so on. And on those faster buses, we have some slower and even some two-wire connected sensor chips, for example, which sense the temperature of CPU and so on, which are really slow. So basically, it is important to find the compromise between number of wires and price of the bus and the actual number of bytes and the required latencies for a given peripheral. Important is to consider who is the partner of the communication of this peripheral. It can be a human for a display, keyboard, mouse, or this can be another machine. So, for example, network communication or some data exchange and so on. And we should consider what is the data rate and what is the peak rate between the I/O and CPU and so on, how many bytes per second is necessary to transfer. For example, simplification, keyboard is input-only device. For example, on your mobile phone, probably the keyboard is really only input-only if it is a keyboard. If it is a touch screen, then this chip usually needs a setup, so it is in the FAC I/O. Okay, so but keyboard, we can say that it is input device. It is from the human, and 10 bytes, 10 keystrokes per second is enough. We can have some robotic sensor actuators and so on, but today peripherals are usually much more complex. They usually allow enumeration, so basically to read some information and identification, what is connected on which port and so on. So at the end, you probably need input and output to work with most of those peripherals. If we look at some requirements for data rates in megabits, in this case per second, and maximum latencies, then we see that something like 100 bits per second is enough for the keyboard, and person will tolerate some latencies. For work with terminal, you can work even with terminal when there is a big clock. My colleague works and tunes a Linux system on orbit, on the satellite, and then he has 200 bytes per second link there, and latencies are horrible and so on, and it is possible to use it. So basically, keyboard is not so critical. With the mouse, the latencies are a little bigger problem, because that feedback between the position of the hand and sensing of the eye and moving the arm and so on is relatively fast, and if you have big luck in this loop, then persons start to position quite imprecisely, but still it is a low amount of the data. If we speak about some voice input for mobile phone and so on, then the data rate can be in some up to some hundreds of megabits per second. In the fact, you can understand to the voice when you have something like 6 kilohertz sampling frequency, and if it is differential encoding, then even 6-bit is enough. So something like 36 kilobits per second are enough for the phone communication. If you want to record music, then you probably want something like 16 bits for the analog levels. You want to have the stereo, and you want for the CD quality, for example, 44 kilohertz per second, the sampling rate. So you get to something like 1.5 megabit per second. If the quality should be a little higher, then we need a little more. In this case, person tolerates relatively big latency in the audio signal, but not a mutual latency between the blocks. So basically, if you have two buffers and one is sent and then is sent another one, and there is some lag in the range of 20 microseconds and so on, you can hear a click. So people are quite sensitive to this. For the scanner, okay, it can need a quite high throughput, but the latency is usually not a problem. For voice output, it is similar again as for the input. For the stereo output and high quality, you may need a little more. For the laser printer, again, you want to deliver quite a lot of data. Graphic displays is relatively huge and high amount of the data, and the people are quite sensitive if there is, for example, a redraw of some dynamic game or some film screen or some snapshot in the middle of the transfer. So there is quite often need to synchronize the image update to a retrace and so on. A cable modem and communication networks can range from relatively small to really high number of bytes and bits per second. If you have 10 bits per second communication link, then a demand for the bandwidth is really high. So in such case, you have no way to process all data on the CPU. It is necessary to store data in memory directly, and then only the visit headers and direct which another card should send data out and so on. So there are accelerators for the computation of cyclic redundancy check codes and so on. So it is relatively demanding. For the magnetic disk, we usually have relatively low latencies of head setting and positioning, so it is something like 30 milliseconds. On the other hand, throughput can be relatively high. If we speak about the SSD disks and this PCI Express technology of their connection, then the latencies are even smaller and data rates are really impressive. And I have there two examples from robotic area. If somebody of you is not directly focused only on the computers as a white or black boxes on the table, but even on the computers which do some control, then, for example, if you want to control a DC motor, then you need it has typically a mechanical time constant somewhere about 5 milliseconds. If it is some modern DC motor with windings and so on, and you need to measure position maybe for 16 bits or even more once per that 1000 samples per second. But what you need to react in relatively short time, in ideally in under the 1 millisecond, with the action which is in the fact voltage which you want to apply to the motor. So you need to have a relatively fast control loop there. And it is interesting to see the development of the computers, because in the past even the PC-grade computers allows to read the data directly, for example, from printer port and write them back and do that precise timing, even in the microsecond range. Today, the complexity of the desktop PCs and those big processors required to switch to the serial buses, and the data are in the fact sent as packets. So latency of today modern desktop computers, when you want to read a single bit and react on that bit and send it back again on some pin, is worse than for the desktop PCs from 80s. So even that the throughput of USB-C and all that buses is really impressive, then if you want to do some feedback back control, then you can get to big trouble. So it worth to decompose the system and move those low-level control tasks to some smaller CPUs which has faster reaction time and lower latencies. If you want to control, for example, permanent magnet synchronous motor in a direct quadratic directions or the plane, so-called vector control, then you usually want to sense 2 or 3 windings current at 20 kilohertz, and in this case you need a higher throughput and latencies even lower, something like 4 kilohertz, 8 kilohertz, or maybe 20 kilohertz sampling frequency. So it starts to be relatively demanding. So it is one of areas where I work and provide the support to another companies. So it is interesting area for me. Okay. If we speak about the software, then on the software level, we have some user application which communicates with another devices and so on, or application, and it wants to have a standardized environment. So you can use some stream operation, NEOS channels on Java and so on, which has relatively high abstraction of the communication. Then you have some user level I/O layer which communicates with operating system. So this one is based usually on something like read, write, open, close, and so on. And then we have operating system interface, which will be part and the description of another lecture, later lecture. And then in the operating system there is some device and even mostly protocol independent generic layer which accepts the request from the user space. Then there is some generic subsystem, for example, for access of the disk in some named hierarchy or on block storage. We have there file systems, then and block management and so on. For the serial ports and so on, some generic terminal function and GPIO function and so on. And then we have there the actual function interfaces of the individual devices, which is already specific to the given kind of the device. And then there are physical device and bus drivers which delivers the actual writes to the peripheral registers and so on. We have there usually some subsystem for the collection and reaction on the external events, so some interrupt handlers and so on. And we can have there a direct memory mechanisms which allows to transfer data directly from the memory to peripheral and vice versa. And then the lowest level is the actual hardware. And I have there some example to have idea how it looks with the complexity on the real system. So this is Linux kernel storage stack diagram. it is simplified but still relatively complex. So if your application use some POSIX low-level operation like read and write, they are delivered to the generic virtual file system layer. It decides which kind of file system, for example, will process and access a given data and provides the support for a given open file and so on. Then we can have there more layers which take care about the mapping. So, for example, you can export some partition or some file as a network device. Another computer can connect to it and build again a virtual block device which allows to access from the local file systems and local users. So you can combine this, or you can combine multiple block devices to form some redundant array of inexpensive disks or RAID to enhance availability, reliability of the data and so on. So it is such block remapping layer. Then we can have there some generic subsystem, for example, for the access of the rotating drive. So it is SCSI interface, which sorts the request, for example, according to the cylinders on the disk and so on, which can enhance the throughput and so on, and lower the thrashing and head movements and so on. And then it delivers data to low-level disk drivers and peripherals drivers, which communicate with actual devices. Or we can skip this management of and sorting when we know that it is NVMe driver. It is PCI, this is this one, PCI and NVMe, I do not see it at this moment, but yes, this one is NVMe. So in this case we skip some layers and it can be even faster. And there are some management interfaces and so on, so it is quite complex. So those are the layers. We look at the simple input-output now, so we get to our concept of the simple RISC processor. In this processor, if we speak about the buses on the chip, then we have there usually the separate write data port and read data. So basically those are two wires or two signals, two set of the signals which are provided as the output from the CPU and input to the CPU. And then we have there the address. So if we want to write to the memory, we provide the address. And if we want to write, we provide the data and they are stored in the memory. If we want to read, we provide the address and request to read, and the data are delivered on the CPU input. And we can add there a component which is called the address decoder. And if, for example, load word or store word instruction address targets the area which is reserved for input-output devices, then we do not enable the memory write for the write or do not select read from the memory, but we decode by this address decoder, usually from some subset of most significant bits of the address. We can control that the given data will be stored in the register at the next clock edge or something like that. And that register then holds the data which are delivered to actual circuit of the peripheral. So for example, there can be bit which can, if it is set in, for example, switch LED diode on, and if it's on the low level, it switch it off or something like that. So in this case, we need to keep somewhere the state of that individual bit and then provide it to peripheral. when we want to read, then in such case, if the target address corresponds to the address of the I/O device, then if we select such address, then the decoder selects that the output from a given device should be delivered to the input of the processor. And if we look at the address decoder, then the logical structure is that basically there is some bus and it has some data and address, and each peripheral responds to some range. In the fact, it is quite common that there are so-called bridges between the faster and slower buses and so on, which separate the buses. And in such case, actual physical structures doesn't look like this logical one where it is a flat area. As for the address decoder, one option is that there is a central address decoder which takes the address from the CPU, and according to the address, it decides if memory should be activated or some peripherals. Or other option, which is quite often used, is that the peripherals has a local address decoder, which only responds or activates the device if the address going through the common address bus and common communication bus matches some of regions where given peripheral should respond. So it is autonomous in this case. Usually in this case we need some mechanism how to set up those addresses that they do not overlap, that the base addresses for the regions of different cards are unique. Okay, it is. We can go into the more depth here, but I'm not sure if we fit in this. And then there is an example of simple speech synthesizer chip. It is all cheap, but you can buy such chip which allows to say some word or some sentence. And it is controlled by a table of alphones where you can say, I want to play a given alphone. And alphones are fundamental units of the speech. So basically those are basic sounds with some binding to the previous and another vowels and so on. And this one is pre-programmed for the English language. And we can, for example, have a simple program where we assume that we have 5 such units placed at this address in the memory, which should be played by the chip. So what we need as the input-output of the chip? We need there bits which allows to select which of 64 alphones should be played. Then we need to have there input which say play now what is on the input pins. And when we start the playing of one sound, we need to wait till the chip finish the playing. So we need to monitor some standby output which informs that now the chip is ready to accept new data. And the chip plays a sound on some of its outputs. So we want to connect this chip to our concept of the CPU. So we have reserved some area from address space, this area starting by FFFFFF00. So if the address on address bus matches this range starting here, then in such case we deactivate a memory write signal and we switch this signal, this multiplexer, to the output of our chip. And if we write to address which ends by 00, then we write in the fact to this register, and it holds then the 6-bit combination. Then, or 7-bit, 6-bit, probably in this case. And then we need to toggle the ALD, and it can be done such a way that we can have there another peripheral register that if we access this address, then the write to this second register is activated. And to read the status, we can have there a rule that if you read from this address, then that bit standby is multiplexed, is fed to the LSB bit of the data bus going to the processor. And so the synthesis, the algorithm is set ALD to 1, so basically inactive. Wait till the chip confirms that it is ready to accept a new Alphone. Then write the 6-bit information on its input, what should be played next. And then set to the ALD to a 0, which starts the playing. And then you came up, set it to 1, and again wait till the standby output informs that next Alphone can be accepted. And this is the code in some processor system which can look like a RISC-V, RISC-V. So what we need, we set the S0 as a base to the area of the input-output registers, because we cannot address over so many bits, so it works to set the base address. Then we say, then we prepare in another register in T1 the value 1 to have it directly on hand if we want to set ALD at 1. Then we say that we want to play 20 bytes in the fact, because it is 5 Alphones multiplied by the size 4 in this case. Okay, maybe it is a waste of the space, but we have it done in this way. And then we say that we want to read a data, okay, in this case from some address. At this moment there is this address. And at this moment we said that we start with the index 0. And the first operation is to store at the address FFFF4 with the offset 4 here, the T1. So basically it set ALD to 1. Then we load the code of the next Alphone from the table. If we have already reached the end of the loop, then we skip to a done. If we have not reached end of the loop, then we add the 4 to the counter of location for the Alphones and load. No, excuse me. In this case, when we when there is we store the LED to 1. Now we load the address 8, FFFF08, where is the possibility to check for the standby signal output. And if it is still 0, if the T5 is still 0, then we know that the chip is still busy. When it is not busy, we add the location in the memory, that offset of the byte, to the base address of the array. This is that T3 plus T. We have T5, and we access data in the table of Alphonse to play, and we store it in T5. And now we store a T5 at the address FFF00, which is the register to hold the Alphonse code. Then we set a 0 to the address with 4 at the end, which in the fact sets the ALD to a 0, and the chip starts to play the sound. And we move to the next location in the memory. And if we are at the end of the sequence, then we stop. And if we are not at the end, we continue then by a next loop. So this is how we can build such circuit. Now we look at the real and use peripheral, and it is asynchronous serial UART, which is a mechanism how to send data. It was initially implemented to send data over some telephone line, phone lines, or through some wires and so on to the modems and so on. And even that it is really maybe 40, 50 years old standard, it is still used. For example, if you have a hard disk, then if you have a documentation, you probably would find that those pins which provides a RX receive and the TX transmit of the data to and from some internal controller on the disk. You can usually find those pins even in your mobile phone internally, which allows to debug the kernel, debug the phone, and so on. So this standard for the serial communication is quite often used, and it is asynchronous. So basically, if you have nothing to send, then there is a steady 1, and then it switches to the low, and there is one so-called start bit. So basically, when we sense that there is a change of the level, then we know that it is the start of the one character which will be sent. Then, if we check at the 1.5 time of that start bit, then we know that there we can read the value of the D0 and so on. So this way, we can read up to 8 or even 9 bits, and even the parity bits, which allows to check if the character has been transferred correctly. So basically, the sending circuit sends such combination of zeros and ones, and the receiving receive it at this middle of the sampling interval. And the sequence is end by 1 bit, which is guaranteed to be a 1. So this way, if there are no more data to send, then there is idle time, and again, when there is again a byte, then you know that data are coming. So this was a mechanism which was used in the past to connect typical terminals to the computer system and so on. Even the terminals on the screen on Unix system are in the fact emulating the terminals which was and has been usually connected by this protocol. So, and it is really simple. So it is a protocol which is used for low-level debugging, which is used as standard input-output in many embedded applications and so on. So we now look at our system. We have our QTR vSIM, and in it we have reserved that area from FFFFC00 is used for the peripherals. So there is a memory is cached, but for the peripherals you usually do not want a caching, because caching means that basically we store some data in the cache, and until it is necessary, we do not write back them to the actual peripheral. So for example, if you write a hello world to the cached region, then nothing appears in the actual register which sends the data out. Or there appears only, for example, the last L when the data are when the location is used for another data in the cache. So you probably do not want to have the caching switch on, so it should be probably uncached. And to send the data over this serial line, we need one register, which is called a TX status, which in our case informed by least significant bit if the register is ready to accept a new byte. At the moment when the register is ready, there is a 1. Then we know that if we write a byte to the data register, then it will be sent to the, it will be first transferred to the transmit shift register, and this sends it byte by byte to the external link. Be careful, this link can be on a 3 volt, 1 and 1.8 volt, and so on. It depends on the different variants. The external RS 232 standard is at plus minus 12 volts. So if you mix the voltage standard, you can damage the chip. For the reception, the bits are first collected in the shift register, and when we have a 1 byte ready, one character ready, then it is transferred to some received data register, and a ready bit is set to a 1. And CPU in this simplest case can pull for this least significant bit in the status register, and when it is set to the 1, it knows that they are actually the data and it can read them. So, how to integrate this to our simulator? So we have there some base address for our peripheral. So it is the first address for the peripheral. We see that exactly this address is the address of the receive status register. So there is the mask which informs if the data are there. Basically, if you read the value by load word and the least significant bit set, you know that in the receive data register we have actual byte. And this is at the offset 4. Then at the offset 8, we have a transmit status register. And again, it informs us by the least significant bit that the register, that the transmit machine is ready to accept a next byte. And actual byte is written to the offset 12 to the C. And we can write it directly to this address, or we can use the offset when we address against some base. So we try to look at the code which writes a hello world. So it is part of our QTR vSIM. So what is there? It first sets the A0 to a base address of the serial port, so FFFFC and so on. Then it loads into the A1 the address of the symbol text1, and at this address we use a special directive started by dot. It is assembler directive, which works such way that it stores a string in ASCII, but the suffix Z means that it is 0 terminated. So if you have worked with C language, you know that the strings are in the sequence of bytes for the C, which is terminated by 0. So this way we have there a string in the memory, and we then load the value to the T1 register from the address, in the fact this H. Then we check if it is the final 0. If it is final 0 character, then we skip and end the loop because it is not necessary something more to write. Then we add the 1 to the pointer to move to E, but we have H still in the T1. Then we load the address which is in A0, so basically base address, plus the 8 in this case, which is TX status register, transmit status register. The combination of offset together with the address points to FFFFFF C008. And we check if the least significant bit is set to a 1. So basically we mask this bit, and if it is 0, then it means that the device is busy, and we need to loop till the peripheral sends the previous character. At the moment when it is ready, then we store the T1, H, E, L, and so on to the data register, and data are sent on the actual link. And then we again continue by next character, check if it is 0, and so on. If you look at our simulator for a non-pipeline version, then you can see, okay, there is a diagram of the simulator. We get to this store word instruction here, and this store word instruction now stores the, in this case, I think this is, I think this is L, ASCII character L, to the serial port, and serial port to the address, which can be seen here. So basically, in this case, there is seen the actual address where to store the register, where just to store the character, and then there is the actual value, which then gets as the L to the serial port. And serial port has there those 4 registers, so we can directly look in our simulator what is in the data registers and the status registers of the serial port. So I tried to demonstrate it. Okay, so this is our simulator. We have there the example, in the examples, template S, and then template S in the fact of writing of hello world to the serial port. We can go to our program, and maybe I will show it this way. So basically we go step by step, and now we at this moment we load the status register, so we check if the value at the register 8 is the 1. And it is the 1. So because it is the 1, this means that there is the ND, 1 with 1 is 1, and this means that it is not a 0, so we can move to the actual store word operation, which stores the character in the register 6. Register 6 is here, 48. It is hexadecimal, which is a capital H, and in stories at the address, which is given by the offset 12 and register 10, and register 10 is here. So when we move to this instruction, then we will see what happens there. You can see that H has been written to our serial port, and if we enlarge this area of our CPU, then you can see that the FFFF has been added together with FFFC00 has been added together with C. So we have got FFFFC00C. It is the address to the memory or to the peripherals. We do not have directly shown each of them separately. So basically this is the peripheral box. And the value of 48 is delivered from the second output from the second register here. And we can see that actual value has got to our terminal. So if I try to write there, for example, 41, it is capital A. 61, it is small a. If I write 31, it is the 1. As you can see on the receive side, we have there a 0 in the status register. This means that there is no character. But if I try to write, for example, there a B, then you can see that at the address FFFC00 is a least significant bit of the status receive status register set to 1. So we know that there are data which can be read from the data RX data register. So we should now understand how the input and outputs works. And if we look at the pipeline version, it works exactly the same, but the actual input-output corresponds to the moment when the instruction propagates to the memory stage. So when instruction is in the mem stage, then at this moment, if it targets memory address, the address where, not memory address, but address where is mapped the peripheral, then the output appears here. So again, we have there an example. So we can select that we want to have the pipeline version. Start empty. And I can delete a content here. And if we step through the code, and this is load by, now we load the value from the status. It will get there to the load word here. Load word now. By the way, now you can see that there will be a one knob, one stall, because we want to use directly a result of the load word, which is necessary to put there a stall to forward it then to the execution phase. So we execute this one, and now we get to the store, and we see that when the store has gone through the load word begin at load word knob and the begin store word. You see that at the moment when store word goes through the memory phase, then the actual write to the output is seen. So if it is even pipelined version, but without some complex out of order instructions, processing and so on, then it is relatively simple that it works this way. Okay, so we have seen what it is possible to do with input-output, and if we build, for example, a C library which redirects a standard input and output to the serial port, then you can start to write the program on the bare metal system which communicates with you over the serial line, same way as if you have it run in the console on the computer. In the fact, the terminal on the computers. That black window is usually, or is in the fact emulation of that serial terminal from the old days. So it works this way. We have the additional set of the peripherals on our simulator, and they start at a little different address at the base FFFFC100 hexadecimal, and those peripherals corresponds directly one-to-one to the peripherals which are then found on the education kit MZ-Apo, which you will use as the real hardware. So if you test how to work with those peripherals on this simulator, then you can use the knowledge for your semestral work. And we have there one register, 32-bit, where we can write a value, and it is written in binary, hexadecimal, and decimal. On the real peripherals, it is shown on the 32 LEDs. So basically, as you write the combination of ones and zeros, then it lights and switch off LEDs. So basically, you can analyze the actual binary encoding of the data. Then we have there two RGB LED diodes where you can write the three components of the color, and there are three knobs which allows to tune three true color three components of true color value. So by each knob you can set the value from 0 to 255. So you can set three consecutive bytes which can be read from this address. So basically you can read the address, and if you read it and write it directly to the LED, then you will have exactly LED with appropriate color shown. And then there is more documentation for the peripherals, so you can find them on the documentation for the simulator, and then you can find it even on the documentation for our kits. And we emulate even a frame buffer, so it is the area of the memory which is shown as the pixels of different colors in some frame on some screen. In the case of MZ-Apo, the small display 480 by 320 pixels is used. And they encode the color only a 16 by 16 bit. So they do not have 8 bits per component, but only 5 for R, 6 for green, and 5 for blue. 6 for green because human eye is more sensitive for the green, so more levels for the green are used here. And there is a start address, so it is possible to test how to work with the frame buffer on a simulator, and then you will try it on the actual kits. And if we generally now speak about the peripherals, then they can be mapped directly into the I/O memory, into the memory space. So this way, as we have seen it in the case of our simulator, that basically in the memory view you see it and you can directly access it by load word, store word, or there are specialized instructions to access I/O. In the past, x86 used mainly the specialized I/O instructions, but today modern I/O cards are mapped to the memory address space, and that I/O is not suggested to be used from the drivers and so on. On RISC CPUs like RISC-V, MIPS, Spark, and so on, the separate I/O range or I/O address space is not implemented. So because some cards still have the I/O specialized I/O regions, it is somehow remapped to the memory ranges. And okay, in each case we have there address ranges which are dedicated to the individual devices, and read and writes to that ranges corresponds to the providing a data to the peripheral, usually writing to some register and reading some registers and so on. And the information, the data are ready, can be provided by this simple bit, as you have seen in the case of our simulator. But this means that you need to pull, basically, you need to block your program and test, are the data available, and so on. So it wastes the time. So usually there is provided some mechanism which allows to inform a CPU that there are no new data by some mechanism called interrupt or exception, which stops some another program which doesn't wait for the data, switch the operating system. It calls appropriate interrupt handler routine, usually in a given driver. And if, for example, the full line of input or something like that is provided, then it passes a data to the actual application waiting for the data. We have seen that there is the address decoder and that there are some I/O ranges. And now we look how it looks in the desktop PCs, which you probably know. So this is the older Pentium 4 based system, and in this case it uses actually the parallel buses where is the address and data and so on. There is some I/O controller hub which integrates some USB, Ethernet, and some other stuff, and then there is an actual processor, and it is the bus which provides us interconnection. Today there is a switch to a much faster serial buses, so you can see there are gigabytes per second, so 2 gigabytes FDI is even more fast, and we have a relatively high-speed connection here, and all integrates to the processor chip together with memory controllers and so on. So basically the things are integrated, and we look how the buses are changed over the time a little later. There is an actual mainboard of some, okay, maybe it is not today, but some modern desktop PC. So you can see that in this case it is old enough that there are still the old parallel PCI slots. Then there are equivalent PCI Express slots which are much shorter, needs much less number of pins, but has similar throughput as those parallel ones. And then there is a fast PCI Express 16 for the graphic card. And then there is a there is a chipset, there is actual socket for the CPU, and the location to connect the memories. And what is in the fact a main task of I/O subsystem? It is the mechanism which allows the interconnection of the subsystem inside the computer and connect external peripherals to the computer. And we need to provide an optimum data path to deliver the data, and there are demanding peripherals like graphic cards and maybe external memories and so on. But on the other hand, we need to keep the price competitive. So for the slower peripherals, the hierarchy of buses provides some slower branches for those slower peripherals and so on. And we need sometimes to lower the price, so it is possible, for example, to share a data and address path, or and so on. So there are some options how to simplify the connection and convert it to something else. If you look, for example, at old parallel disk, parallel connection, then advanced technology attachment, okay, but in the fact it is already quite old technology. Then on this connector you really find 16 signals which delivers a 16-bit information to and from the disk, and then there are some pins which corresponds to some subset of the address and so on. For the higher speed, if there is used 80 leads variant, then each second is shielding, but it is not so important. But today there is a switch from the serial solutions to the from the parallel solutions to the serial. So it seems not so logical. You think, okay, serial, I send only a single data bit per a given instant of the time, so it would take much longer to send a whole byte than if I can write it in the parallel. This is right, but at the moment, when you want to deliver, for example, data on something like 64 wires in parallel, then you have problem that the delivery in the time over each of those signals path, over each of those trays on the PCB and so on, takes a different time. And if the times differ, length of the signal differ or some physical features of the path differ, then there is a problem that if you want to send one word after another fast and then receive them on the other end, that basically there is no instant in the time where you can sample a given data. I have there some example, and this part is important. Basically, it is not important to remember that there is ATA and PATA and so on for SATA for you at this moment. Okay, it is important for you if you build a computer or want to understand the technology, but not for the exam. But for exam, you should have a basic idea what is the problem of the parallel buses. And I have there some example. So basically, you can see we have some finite speed how data are delivered over the wires, and in this animation we see that for example now are sent red data and they are delivered at the second target end of the link now, and now if you sample and deliver there some clock or something like that, now green, now you can sample a blue and so on, then there is no problem and you can get data on the parallel bus. But at the moment, when we have we want to send more data faster, then in this case, you see now we have sent red bits of red word, but as you can see, it reached the other end of the link intermixed, because on each of those links, data are delivered at different instant of the time. Yes, this is the effect that the speed of each link is different, or it is same if it is proportional speed, for example, against the length of the links, and those links has different signal paths, different length. So basically, you can find that there is no possibility to sample at some instant of time all the red, all the green, and so on, because they are intermixed in the time. I hope that you can see it. So it is a problem, and for this reason, at the end, the parallel buses are replaced today almost in all those high throughput channels by the serial ones, where we can go to much higher frequencies. We get to that it can be something like 40 giga symbols per second and so on, really very high frequencies. And if we can use something like that mechanism which you have seen on that slow serial link, which only send 1 bit in the time, then in the fact, thanks to the much higher frequency or bit rate, we can transfer in the fact data faster than on the parallel bus, where the delivery at the same time is not guaranteed. So, for example, for PCI Express, we can deliver over the one link something like today 8 gigabits per second over single link or something like that on PCI Express 4. So it is quite fast. Same for ATIAs, which was parallel in the past, and now it is this serial connector, which has one link formed by two differential signals, we get to this later, to the one end, one direction, and the second one is a return path. So basically we have dedicated links, 2 wire for each signal. It is sent as differential, and we can go to the frequencies which are much higher than for the parallel buses. On the other hand, if you send the data over that serial bus, you need to add there some synchronization, some start of the frame and so on. So it doesn't work so well for the random access, for example, to the memory. So in the fact, still main memory of the computer is connected through the parallel bus, because it allows to deliver data and address in parallel and with lower latencies, or almost parallel. So it is interesting but for the PCI Express, HDMI, SAS technology, and even today, for example, for new version of the SD cards and so on, those fast differential links are used. Okay, now we return back to the interfaces and actual peripherals. So what it is interface, the definition? It is some communication part, some border between two mechanisms how data are delivered. So for example, it can be interface between a memory bus of some computer system and then this serial link where we send a data serialized. Or it can be interface between again computer system and the controller or interface which sends data to the actual hard disk or SSD disk and so on. So basically it is that border where, or boundary, where we change how data are delivered and who is controlling the actual delivery and so on. We can have a bus which is a setup where we have some wires which are connected to more interfaces, and through some address we select which one should be activated. Or we can have a set of point-to-point connection. We usually have for the parallel buses separate address and data bus and then the control bus, or at least we need those 3 parts. On the serial ones, we somehow multiplex all this on the single link thanks to some structure of the packets. And the buses can be this separate, or it can be multiplexed to lower number of the wires. They can be local to the system, or they can be the external and so on. And we need to know what it is a bus cycle and bus transaction. So basically, the bus cycle is that we address usually or request some data and wait for the so for the data, and there are multiple transactions where we exactly get the individual data words. And we can use a different technology for the signaling, so it can be bidirectional wires, or it can be a unidirection and another set of wires for the backward path and so on, and switch it, multiplex it, and we usually use term initiator, so it is that who requests data read or write, so basically who controls what operation should be proceed, and then the target, which is the peripheral, which obeys the order and stores the data or delivers data according to the initiator requirement. And we can have different topologies. So one option is that we have the real shared bus, and if we share the signals to connect more components together, then we need to have there some mechanism which allows to arbiter who is in the control of actual link at a given time. So basically only one transfer can proceed at the given time. If we have point-to-point communication, then for example this is full point-to-point with each other. So in this case the communication can be ongoing in parallel, but it is quite expensive. So if you have more nodes and you want to connect each with another one, then it is too expensive. So we usually use some tree structure or something, for example, like USB bus with hubs and so on. And if we return to the simple synchronous bus, then we have there some bus clock, as we have for our computer processor and so on. And for example, in this case, at the racing edge, we set the address which we want to read. We say that in this cycle we want to read, and in this case, at the falling edge, data from the peripheral or memory are delivered, and we can read them, for example, at this clock edge. And then if we want to write, we select, okay, next cycle is writing. We define the address and data which should be written, and we can reuse even the same signals. So it is a classical parallel bus with separate address bus and control bus, which consists from the read, write, and clock, and the data wires, data signals. And this is synchronous. We can have even the asynchronous buses. They do not need exactly the clock. And in this case, for example, we select, okay, we require the some transfer, data transfer. We need to set the address and data. And, okay, first we set address, data, then that we want to, for example, write. And then we say now is the start of the request. And the target device informs, now I have ready, I have taken the data from the data bus and the address. And at this time we can negate the request, and the acknowledges negate in the response. So it is possible to build the asynchronous buses as well. We can have even the asynchronous bus which has, for example, the signal which informs where to strobe the data. So it is not synchronized directly with the clock, but it has a special signal which provides the timing where data should be taken. In this case, you need to assert the strobe for at least some minimum time that you know that the information propagates to the peripheral. And now we look again to our PC. Not that PC is some interesting system, but it is quite often used. So you sit here by the PCs, so why not? So the original, okay, or 2000 PC on of that time has basically some RAM connected to the memory controller hub to the CPU, and CPU has some parallel front-side bus bridge, and then a PCI bus where the wires are or signals are parallel connected to the different devices, and we can communicate with those one which responds to our address. But due to these problems which I have shown on the screen, on the animation, the originally parallel PCI bus has been replaced in the system by the switch and the point-to-point links with dedicated lanes in one and another direction. So data path. And same it is for the connection of the processor with root complex and so on. So basically everything is now switching to those very fast serial communication. I'm not sure if we get to full depth. And it is not necessary for the exam. So for exam it is important to understand the problem of parallel buses. And now a little how parallel buses works in the day of PCI, which is history, but same way, for example, works or similar way on AXI parallel bus works the peripheral inside your mobile phone and so on. So if you look at for the PCI bus, then it is a physical bus. It interconnects most of the signal directly through all the slots. And we have there 32 signals which are used to send the address and data. And they are bidirectional, so we can use them to deliver data to peripheral or the back. Then we have there 4 signals which select which octets from the 32 bits should be BE0, I think that is BE0, BE1, BE2, and BE3. So basically, by those byte-enabled signals, we control which bytes are exactly delivering data, and those signals are used even to send the command at the start. So we do not have there a separate signal that we want to write to peripheral, to the memory, read, and so on, but it is encoded in those 4 bits at the start of the transfer. There is parity to check for the data integrity, and there is a control. And there is a most important signal, which is a frame, which informs that the bus cycle or frame starts. And then there are 2 signals for the initiator ready and target ready, which controls where a device is ready to transfer data. So even that the bus is fully synchronous with the clock, all operations are in synchronous with the clock, then the bus is pseudo-synchronous in the fact, because if the peripheral is not ready to accept a next data word, then it can say that it is not ready, and the initiator needs to wait one more cycle. Then there is the information which sends the device that it has been selected. Then there is a possibility to select devices, or they control space and identification based on the individual slots. So this allows enumeration at the start. And then we have there some errors reporting and request for the bus, because bus is shared, so it is necessary if, for example, given a hard disk controller or interface card wants to write to the memory, then it needs first to ask, I want to have a control over the bus. It is confirmed by the ground signal, and then it can run its own cycle to deliver data to the memory. And then there are interrupts to deliver the asynchronous event. And you can see that there is large set of the different PCI Express cards from the networking and audio, video, and so on. This is the actual list of the signals on the bus, so you can find that there are the power supplies voltages. We can find there those AD signals with actual data, CB, those byte enable, and so on. We can find there those requests for transfers and for the bus and so on. It is not important, but you should be able to read the timing diagram. There is even the variant with 64-bit bus, and it is possible to go from 33 megahertz to 66 with some peripherals and so on. It is not so important. Important is that you have some idea that if we have a parallel bus with signals which go through all those slots, and that we have there the some, in this case, combined address data signals, some control signals to control which bytes and which operation should proceed, and then some another rest of the control signals. And there is that ID cell mechanism which is used during the initial enumeration of devices. Basically, you ask what is in this concrete slot plugged in, and you can read some address range and find who is a vendor and what is the device and what are the capabilities and so on. Then there is that arbiter which accepts the request from the different devices that they want to do a transfer and grants them the bus. So basically it grants that they can drive those signals on the bus, and we look at actual transfer. Important is, in this case, we have the role if the initiator, it is that one who has won the arbitration of the bus, and the target which obeys the order. We sometimes say that initiator is bus master, and the target is obeying the commands. So initiator and the target roles doesn't directly impose a data source and receive role, because if you are initiator for the read command, then in the fact you receive a data later. And because this bus allows to delegate a right to send or control the bus to devices, then for example you can program this controller to do the actual transfer of the data from some sectors on the disk to the memory. And then you do not need to take care for it from your code, because hard disk controller basically asks for the bus, obtains the bus, and stores the data to the memory. And then only when one or more blocks are sequentially read from the disk and stored to the memory, that at the end, when it finishes its operation, it interrupts the event and informs the processor that, or operating system, that the transfer has been finished. Bus signals are shared, so only one device can act as a master in this case, and there is the arbiter which is implemented on the main board in this case. There can be even some decentralized mechanism and so on, but all transfers and signal exchange and so on and sensing is done on the racing edge of the clock signal. So this is the event where you care about the data and where you set a new data and new values on the bus. And the bus cycle, in this case, whole is formed by the address phase, where we inform if we got the control over the bus from the bus arbiter, we can say, I want to communicate with device and register at this address. And then there is a data phase where the actual data are transferred. It is even possible to transfer not only a single data word, but a multiple of them. So something similar to the burst for access the memory, and it is pseudo-synchronous. And now this is a critical. So basically, this is how it looks if you look at the time diagram. So basically, it's what happens in the individual instant of the time, clock by clock, and so on. And we have there more okay, there are the kind of the transfers which can be used. So we can have this is on those 4 signals which inform that it is, for example, the access to the memory at the given address. And it is read, write, or that it is read or write to the I/O input-output space or peripheral. Then we have there the information, for example, that a next transfer has dual address phase, so that it is a 64-bit transfer. We can have there some another kind, for example, acknowledge of the interrupt and so on. So those are different kind of the transfer. Important is that we do not have there only I/O and memory space, but, and this is the thing which you should remember, there is some control space which allows to identify the cards plugged in individual slots. So it is important for the initialization phase. And the actual transfer, if it is without the blocking, then it starts by the, in the fact, this is asserted the frame signal, but it is a negated signal. So it is active by the logic 0. And when it is asserted by the initiator of the transfer, it sets the address and a command, for example, in this case, a read operation. And so this is the start of the frame. And at the moment when the address and command is confirmed by the next rising edge of the clock, then all peripherals connected to the bus check if the address on the bus is matching their input-output region, or their region, and that it is a given command. So basically, that this match their operation and so on, and they addressing. And if a given device recognizes that the address and input, output, and so on matches their region, then it informs back by def cell signal that the device has been found. And then there is one cycle where both initiator and target informs by the not asserted level, by inactive level of the ready signals, that it is necessary to wait for a bus to switch from the input to output, or for device, and from the output to input for the initiator. And then when both are ready, then on each clock cycle we have their transfer of one data word. And when the master, or when the initiator, so basically this is both are ready, they say that they are ready, yes. And now we transfer words. And when the initiator decides that it doesn't need more words, that the next transfer is last word which it wants to read, then it deactivates the frame signal, so it sets it to logic 1. And this means that next clock cycle there is a transfer of the last word. If we want to transfer only the one word, then in the fact the frame signal would be deasserted here or there. So no, there. It needs to be deasserted there. So basically it informs that this word is the last word, and there will be no more words transferred. So it needs to be asserted there or there. And this means that it is only the single word. So basically the last transfer is done at the time when the frame is not active. And then both disconnect from the ready signals and default it deasserted and so on. So you see that that frame signal is deasserted before the last word transfer, and we can delay the transfers by inserting not ready condition, the wait condition. So for example, for the writing, we say, we want to write the data to this address. We set there that it would be a memory write command. And then by BE signals, we say which bytes will be written at the given clock cycle and provide the data. But when initiator, for example, processor, is not ready to deliver a data for some reason, it needs a cycle, for example, to refresh memory or something, then it can say, okay, in this cycle, I do not want to deliver data. Even the target can say, in this cycle, I am not able to accept written data. And the initiator now decides, okay, next transfer will be the last one. So it sets the frame signal. Now, still the target say, I am not ready for the data. Wait, please, and so on. And at the moment where it says, okay, I do not wait any longer, I can accept the data, then in this case, the last data word is transferred. So the last transfer is here, and at that time the bus is released, and again there is a time by those two arrows shown where where a role of initiator can be changed and some different device can connect to control the signals. And for the read, it is similar. So basically we say we want to read by some command, by combination of those 4 bits. Then we say the address from which we want to read. But in this case, there has to be one cycle at which there is no data transfer, because it is necessary for switching of those shared wires from the role of the address from the initiator to the target to the role of the data path from the target to the initiator. And again, when the target, so basically that one who delivers a data at this moment is not ready, it says, okay, wait for me, please. So in this case, data are not delivered at this, and they are delivered only when both are ready. And again, they are not delivered, but this is the last word, and now they are delivered to the initiator. So you should be able to read such diagrams. You do not need to remember them, that you are able exactly to reproduce them and write them. But if you get the diagram like this in the exam, you should be able to show what happens there. There are some rules how the asynchronous events are delivered, and we have there even the seminar where we exactly measured on the buses in the PCI system. There is a large problem with those parallel buses, which I have shown to you before, and there is even problem if you interconnect the devices by a single wires, a single-ended signaling, that basically if there is some, for example, high current and high power consumption peak in the graphic card, then in the fact voltage drop on the grounding interconnection means that basically the levels can easily become the ones can become 0 or vice versa. So for this reason, if you have single-ended direct signaling in one or another direction, or even worse, even in the with the bidirectional solutions where you switch role of the wires and signals, then it can be a big problem. So for this reason, we usually use differential signaling for the higher frequencies, where we can lower a voltage, and 1 and 0 is defined as the definition if one wire has a higher voltage than another, or if it is vice versa. It has big advantage that in this case, if you shift a grounding level, then there is not so big problem. Even the electromagnetic interference, if the both wires, the pair, is routed together and kept together in the cables and so on, that both signals are influenced the same way. And if the receiver part basically only compares the value between the one and another signal, then even if it is shift up and down, there's still the condition to decode 1 and 0 are kept. So this is the reason that we use those differential signaling. The voltage level, actual voltage level, are lower and lower. There is a single-ended signaling, classical signaling, which has relatively high. It is prone to the interference and so on. And if we go to the PCI Express, then it has been shown that basically it is hard to have a parallel buses which has a higher words rate than 1 gigahertz, so that the delivery of such signal in parallel system is problematic, and that you do not have the time when you can sample it and so on. So, but if we encode the data on the single pair and we reconstruct the timing exactly from those data, we can get to something like 12 gigahertz on the Cooper standard signaling. In the fact today, as I have said, for example, NVIDIA and NVLink connecting it to the PowerPC chips can go to something like 40 giga symbols per second. And in this case, if we want to increase the throughput from that single bit in time, even that it is very short time, then we can put lanes in parallel and send a first or one lane, second byte on second lane, and so on. So basically we send the data in parallel. So today we switch to the PCI Express, and for sure in this case we cannot have the parallel wires, but we need to have the dedicated channels to connect each endpoint in one and another direction. So, but from the operating system point, it looks same, and it is compatible with the PCI standard, which is nice. And it will be for a whole another lecture. There is what it means, how the signal is disturbed in the time, that there are problems that after, for example, 11 meters, you have even the fast signal basically becomes the flat signal. And and for this reason, we try to deliver the signal which is well shielded from the rest of the system and so on, and we use this differential signaling. So basically we have there a serialize where we put the data, it sends the bit by bit at very high frequency, it is necessary, okay, this is how looks the signal on the transmitter. So basically it looks ones and zeros goes this way in the time, and when it is on the other end of the some longer connection, then basically you can start to have the problem to distinguish what is 1 and 0 at this time. So basically, if this is the time when we want to sample the signal, it is still possible to sample 1s and 0, and in this case, basically, we lose this option. So it is necessary to optimize it. We have the lanes, we can put them in the parallel, and so on. This is description of PCI Express. And the actual signaling requires that we can reconstruct the clock, so it encodes a data by in the fact 8 data bits are encoded for the standard PCI Express version 1 into 10 bits, and it ensures that there is at least some change during the data byte transfer, so it is possible to resynchronize. And even it ensures that there are balanced number of zeros and ones, so the signal can be sent only as an AC component, even on the over the connection connected through the capacitors and so on. Okay, so I have there quite a lot of other details. There are the speeds. So basically, the standard PCI sends 32 bits at 33 megawarts per second. So it is 33. It is something like almost. Okay, what it is? 33. Yes, it is, but it is bytes. Okay, so it is almost 1 gigabit, but divided by 8. So it is something like 100 megabit per second for the classic PCI. PCI Express switches to 2.5 gigahertz clock, which is raw signaling, and it allows deliver 200, okay, with some overhead and so on, it can deliver something like efficient data rate is 200 megabytes per second. So even that we have switched from 32-bit width bus to 2 wires in one direction, 2 wires in another direction, we have increased the throughput. And if we go to the PCI Express 3, it has 8. PCI Express 4 has again 16 gigatransfers per second and so on. And the encoding has been changed and so on. So the throughput is increasing in the time. And there are some comparison and so on of the technology. This board which we have there and which allows us program a PCI Express peripheral in the FPGA and so on. So, and the software model is in the fact the actual access to the configuration and so on is exactly the same or almost same on the PCI Express with serial communication like on the PCI with parallel 1. But the data are sent as a packet with some integrity and sent over the multiple lanes. So you see that there is overhead. So if you want to write in the burst a long block of the data to the peripheral, then it is no problem. But if you want to read a single bit, control according to it, and write it back, then a PCI Express is quite problematic. This loop takes something like 2 microseconds, even on the fastest computer, to read a single bit from some I/O card and write it back to that I/O card. Which is, if you compare that at the same time, you can transfer 200 bytes if it is a stream. Then it is interesting how slow, in the fact, how high latencies are. Okay, and then there is some description, and it is USB-C and so on. So I think that I will finish the presentation here. There is seen how the bandwidth is growing in the time, and as actual core speed and the number of instructions per second is now seems to be limited. The actual frequency of the processor is almost limited as well, even that there are 5 GHz chips now. Memory bandwidth of the main memory is limited now by the physical reasons and so on. It seems that actually communication are now at their boom of the throughput. Okay, so it is all for the today lecture. Thank you for attendance.